In this video, I'm going to briefly explore the general idea behind numerical simulation of turbulent flows. I will focus specifically on large eddy simulation and assume that you have some backgrounds in turbulent flow, turbulence characteristics, and statistics, and in particular, that you are familiar with the Kolmogorov energy spectrum of three-dimensional isotropic turbulence. Finally, some knowledge of the RANS, Reynolds-Averaged Navier-Stokes approach is required. In this figure below, you can see an example of turbulent fluid flow containing various turbulent eddies. But what is turbulent flow? It's a type of fluid flow in which fluid particles interact and mix in irregular fluctuations in various directions and speeds. In such flows, the velocity and pressure undergo rapid and unpredictable changes in both space and time, leading to the formation of turbulent structures such as eddies. Turbulent flow is common in natural and engineering systems such as the ocean, atmosphere, combustion processes, and more, and is typically associated with high Reynolds numbers. The Reynolds number is defined as the ratio of inertial forces to viscous forces. I mentioned eddies earlier, which are formed in turbulent flows. Eddies are swirling motions with irregular and chaotic structures that vary in size and shape. They are responsible for transport of momentum, heat, and mass, and may have a size ranging from several meters in atmospheric flows to fractions of a millimeter. By this definition, let's explore how to model turbulent flow. We can model turbulent flow by numerically solving the Navier-Stokes equations, which are a set of partial differential equations for momentum, temperature, and other scalars. While I won't explain the different terms of this equation here, I would like to emphasize the importance of the second term on the left-hand side of this equation, which is called the advection term. The advection term plays a significant role in the modeling of turbulent flows, as it is responsible for the transfer of energy between different scales and the mixing of fluid particles. If we discard the advection term, the Navier-Stokes equations would only describe laminar and smooth flows as shown in these figures. Therefore, the Navier-Stokes equations cannot describe transitional and turbulent regimes, and there is no chance to capture any fast motions within the fluid as shown here. Now, let's discuss the fascinating topic of numerical modeling of Navier-Stokes equation. The first approach is called Direct Numerical Simulation, or DNS. DNS solves the Navier-Stokes equations without any need to model turbulence, and it is capable of resolving eddies of different sizes and shapes by using very small grids and model time steps. It can resolve scales from the integral scale to the Kolmogorov scale. there is a question of what the relationship is between eddy size, shape, and model grid cells. Assume an isotropic eddy as shown here. To spatially resolve this eddy, we need 4 cells as shown here. With the grid cells shown here, we can resolve the largest eddies with 16 cells and the smallest eddies with 4 cells. By largest and smallest, I mean the eddies that the model with these cells can resolve. This mesh can also capture anisotropic and non-circular eddies. However, the DNS approach has its own limitations. In turbulent flows with high Reynolds number, the eddy sizes can vary between 10 and 100 micrometers. Resolving such small eddies necessitates an extremely large number of grid points. Furthermore, eddies in high Reynolds number flow that are extremely fast may have a frequency of around 10 kHz. Resolving such fast eddies in time requires extremely small time steps in the DNS approach. Another issue of DNS for high Reynolds numbers is the urgent need for very sophisticated and higher order solvers for the advection term, which is responsible for energy transfer and exchange between large scales and smaller scales. Before starting detailed discussion about alias, I draw your attention to a visual comparison between DNS, alias, and RANS in the following figure. It can be seen that DNS provides the most accurate results, but it's computationally expensive. Alias is less accurate than DNS, but more affordable, and RANS is the least accurate but the most efficient one. Let's now dive right into our main topic, which is alias. The principal idea behind the alias approach can be partly referred to as the Kolmogorov statement, which provides an important framework and basis for alias. In alias, the large-scale eddies are resolved explicitly, and the small-scale eddies are modeled. The modeling of small-scale eddies is based on the assumption that they follow the statistical properties predicted by Kolmogorov theory. In simple terms, large-scale motions depend on geometry, while small-scale motions have universal properties. The Kolmogorov wave number spectrum, also known as Kolmogorov minus 5/3 law, is a mathematical relationship that describes the distribution of energy in the turbulent flow of fluid at different wave numbers or wavelengths. Wave number as frequency in space is defined by this relation, which lambda denotes the wavelength. By resolving only the larger scales shown in the red area and modeling the smaller eddies shown by the green color area, alias substantially reduces the number of grid points required for the simulation, leading to an extreme computational cost reduction compared to DNS. However, alias requires a more sophisticated subgrid scale model which introduces additional computational cost. In order to apply a scale separation, defining an appropriate cutoff length is key. For example, if we assume a cutoff wave number of 10, it is equivalent to an eddy size of approximately 0.6 meter. Alias will explicitly resolve all spatial scales larger than 0.6 meter and parameterize all scales smaller than 0.6 meter through subgrid scale modeling. I categorize the alias algorithm into 4 steps. First, after setting the cutoff length, we need to set the spatial low-pass filter. This allows us to decompose the flow field, for example velocity, into the resolved or low-pass field shown by U bar and the unresolved or subgrid scales shown by U prime. By inserting this decomposition into the Navier-Stokes equations, we obtain the alias equations that contain new terms for the subgrid scales. After parameterizing these terms, we apply an appropriate numerical solver. In large eddy simulation, the low-pass filter is often implemented as a convolution operation between the flow field of phi and a filter kernel function, G. The filter kernel function acts as a smoothing function that removes the high-frequency components of the original field phi. Using the defined cutoff wavelength, the convolution is expressed by this integral that represents the area under the curve of the product of 2 functions, as one of the functions is shifted by the variable r. The result of convolution is a new function that represents the combined effect of the 2 original functions. Note that there is a consistency condition, as shown here, which is indicated by this constraint that G must satisfy. Different types of filters, such as Gaussian and box filters, are used in alias. For example, a uniform weight is given to all grid points within a specified window size in the box filter, which is defined by the alias cutoff length scale. On the other hand, the Gaussian filter kernel is a continuous, smooth function that has a bell-shaped curve. This figure shows how a Gaussian filter with a length of delta smoothes out the fluctuating signal. Filters can be applied in large eddy simulation explicitly or implicitly. By solving this question here on this slide, you will learn how the large eddy simulation applies the filter implicitly based on grid size and finite difference operator. Now, let's dive into the meaning of implicit filtering. Traditional LES models are based on implicit filtering, where the discretization operators and computational grid act as an implicit filter for the Navier-Stokes equations. These models do not require the application of any filter function. The explicit filtering approach uses explicitly filter function and is capable to minimize the impact of discretization errors in finite difference code. By applying the Large Eddy Simulation decomposition into the Navier-Stokes equations, the LES equations are obtained that contain the subgrid scale stress tensor. This tensor is an important quantity to capture the effects of small-scale turbulent motions on the resolved scales of motion. The SGS stress tensor is typically represented for the velocity field by this relation. I should point it out here that in LES, the subgrid scale models should be Galilean invariant. It means that they should be invariant under a Galilean transformation to avoid unphysical results. By Galilean transformation, I mean operations like shift a variable by a constant value, rotation, multiplication, and others. This is important because the small-scale turbulent structures that are parameterized are often in motion relative to the large-scale flow. If the subgrid scale models are not Galilean invariant, then their predictions will depend on the reference frame in which they are computed, leading to unphysical results. There is another point in this figure known as energy backscattering. Let's explain it. During energy cascading, energy is transferred from large scale eddies to smaller scale eddies through the cascading process. However, at subgrid scale, the energy transfer occurs through a process called backscatter, in which the energy is returned from small scale eddies to large scale eddies. This process can affect the accuracy of the simulated flow field, particularly when the flow is strongly nonlinear or when the grid resolution is relatively coarse. For the sake of simplicity, I will introduce just two types of dynamic subgrid scale models, Germano and Leonard. The Germano model solves a nonlinear equation that relates the subgrid scale stress to the resolved velocity gradient. The model is relatively simple and computationally efficient, but can be sensitive to the choice of filtering method and grid resolution. We see that the total stress is decomposed into three stresses, referring to the interactions between large eddies and the small eddies shown, large eddies or scales shown by LIG, the cross interactions between small and large scales indicated by CIJ, and the interactions between small scales shown by RIJ or subgrid scale Reynolds stress. In the Leonard model, an additional term is in momentum equation is added that is proportional to the resolved strain rate tensor. This model is relatively simple and computationally efficient and can resolve important features of turbulent flows. However, it is less accurate than the Germano model. Models of subgrid scale typically involve closures that relate the subgrid scale stress tensor to the resolved velocity field and can be based on physical arguments such as the scale similarity hypothesis or the eddy viscosity concept. In this formula, we show the eddy viscosity representation based on a Smagorinsky relation. The Smagorinsky introduces a new turbulent eddy viscosity that determines the amount of energy that is dissipated by the unresolved scales and is determined based on the grid size and the local velocity gradients. It is noted that the Smagorinsky model cannot address backscattering of energy from small to large scales. To conclude this video, I want to introduce another term known as the subfilter scale, which is used in conjunction with SGS. When using explicit filters, the turbulent flow is divided into resolved, subfilter, and subgrid scales. However, when using implicit filters, only subgrid scales is introduced here, beside resolved scales. Briefly, subfilter scales are resolvable scales below the filter width and cutoff wave number Kc, as shown in this figure. In the literature, this stress is sometimes called the resolved subfilter scale. Several studies have shown that better representation of the SFS stress improves the prediction of mean velocity and turbulence intensities by the LES model.